Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Welcome. And to answer the most important question that has been asked so far, yes, I just Googled it in the last 10 seconds. As of yesterday, it is summer. So
Yes.
there we go.
Hello, everyone. Welcome to another episode of Ask Us Anything about electrochemistry. I'm Alex. This is my colleague Neil. We're two chemists, chemical engineer at Pine Research Instrumentation. We make scientific research equipment, and we try to answer as many electrochemistry questions as we can during these live streams. So we host a lot of webinars, YouTube videos, just phone conversations. I've been doing a lot of workshops lately, and we found that we get a lot of questions either over the phone or on YouTube comments or during webinars. And we have found that we wanted to spend a little bit more time trying to answer these questions, really focus on them, because sometimes those other venues or writing a comment in YouTube is not enough to really answer your question. So we have this live stream where we try our best to answer your questions about electrochemistry. In our experience, we have found that questions that are a little bit too specific or too broad might not be the best use of time on the live stream. But if there's a concept in electrochemistry that you're trying to understand, or you need help with understanding a very specific problem, how to tackle a research problem, those are questions that I think we can offer a lot of advice and value for. We usually do this for about 2 hours. So it's 1 p.m. Eastern Standard Time. We'll probably go to about 3 p.m., maybe a little bit earlier, as we actually have a meeting after this. Type your questions into YouTube or on X, and we'll see them, and then we'll try our best to answer them. We will apologize in advance for mispronouncing anyone's name that comes up, because it's your Twitter handle or it's your YouTube account name. And so we will apologize in advance for doing that. So what is it? Oh, yes. So Chris Georgie says that one of these days I need to. Yes, I do. I have workshops and meetings and stuff until August, so it's not going to be until after August that we make some.
I can speak in Alex's stead here, because he never toots his own horn, so it's up to us to do it for him. Alex makes all the YouTube videos on our channel, like just this man right here. That's it. Nobody else. Like I do, we do this together. We do this live stream. I do the webinars mostly on my own, but like all the YouTube videos, the brilliantly edited YouTube videos that you see, including that intro video, this man does all of it, like 101%, the extra 1%. It takes a really long time, and he's very busy. So if we can clone him, he'll get like a lot more videos done.
Yeah.
But as we always say around here, in our infinite spare time, we'll get it done, which is to say we have none, but it's infinite. So yeah, for sure. I think off the top here, I want to get to a couple of questions that were like quite literally asked as I was finishing last week, which I went like 30 minutes over anyway. I really appreciated it last week for those who joined me just by myself as Alex was out. And I think this question from Deeptanshu had asked, again, right as I was finishing, I didn't have time to get to it. So if you are here now or watching later, I did want to get to your question. We try not to leave anything unanswered, of course, although we're not perfect. But in any case, you asked, how do you select the frequency range when doing impedance? So I'll try to answer this first here for you, and it's hopefully a relatively simple answer. And as a rule of thumb, first of all, it will depend on, of course, the instrument you're using and what its capabilities are. Most commercial potentiostats that can do impedance can go up to about a megahertz, some maybe 500 kilohertz or in that range. But typically, you can assume to start at about 1 megahertz, anywhere from 100 kilohertz to 1 megahertz. That's a good starting point. You want to start at the highest frequencies. Okay, so that's your good starting point. Also another sort of general rule, there isn't usually a lower limit, right? Because as you get slower and slower frequency, well, that's eventually you're just kind of doing cyclic voltammetry almost, right? Your sine waves are so slow that it's just like a DC method. So the lower limit is often determined a couple of ways. The first is, how stable is your system? Because the slower you're scanning, the more unstable it can be, and the more instabilities can play a bad role in your data. So that is just like if you're doing like 1 millihertz, right? That means that each sine wave takes 1,000 seconds. So if you're doing like 3 sine waves, it takes an hour, 3,600 seconds, basically, right? It just takes a really long time. So to a very large degree, you're sort of thinking about the question, can my system sit for an hour and be stable, like in the same condition, same steady state? It's not drifting, it's not anything like that. Not every system qualifies, under that criteria. Some do, but some don't. Okay, so that would limit your lower range. The other is your sanity, because I'm not sure about you, but I'm not interested in a 90-hour electrochemistry experiment. I love electrochemistry, but not that much. So, in all honesty, right, is that to a certain degree, I'm being silly, but the more low frequency points that you wish to do, the longer the whole experiment will take. And in addition to being irritated watching and waiting for it to finish, it also will just reduce your ability to get more testing done. If one impedance experiment takes an hour and a half, well, you can't do a lot of experiments in a day if that's how long it takes. Now, if that's what's required, then so be it. But all of that is to say, a good rule of thumb for a lower limit of your frequency range would be probably 100 millihertz and no lower, right? 100 millihertz means that each sine wave takes 10 seconds. It's not too bad. So again, as a broad frequency range, you can try to use 1 megahertz down to 0.1 hertz or 100 millihertz. That's a good overall range. As you begin doing impedance on your experiments and observing the behavior, you may find that 1 or 2 decades of the high frequency are irrelevant. They'll be noisy, there'll be artifacts, there'll be not really useful data. So you might be able to get away with starting at 10 to 100 kilohertz. And then again, you might also discover actually either direction. You might discover that the lowest frequencies start drifting and get a little bit inaccurate. And so you can tailor that off to go down to maybe 500 millihertz or even 1 hertz. On the other hand, if your system is quite stable and you're really trying to study those effects at the lowest frequencies like diffusional effects, and you really need to clarify them, you might need to drop it even more down to 10 millihertz. The only situation where you would probably need to extend the upper limit as opposed to tamping it down, like I said, would be if you're studying solid state systems. And those typically go up to 10 megahertz or higher or something like that. And not every equipment is even capable of that. But most systems with electrochemistry, which are aqueous, fuel cells and batteries and mostly liquid phase kinds of systems, usually above 100 kilohertz in general, there's not a lot of useful information. So there you go. Those are some advice I guess I would give you for picking your frequency range. Do we have any questions now?
Yeah, we have a
Suppose we
few
do.
questions. Chris did ask one
Okay.
random off the cuff question. I guess we can answer that quickly because Chris is our boy.
That's right.
This is this is just a offhand question. Any thoughts on selecting a reference electrode for glycine based systems? I have not worked with glycine per se, but it looks like it's just an amino acid. And I'm assuming, really, I think the question is like, all right, are you in an aqueous or a non-aqueous system? It sounds like you're in an aqueous system if you're going to be studying glycine. But, and so if it's aqueous, you can go with things like a silver chloride, or you can go with saturated calomel, for example. Of course, I don't know if chloride or sulfate, for example, or mercury sulfate for aqueous systems is helpful or useful or plays a role, or if the ions of the reference electrode will do something to the glycine based system. I also don't know whether or not, what are the other electrodes that are being used. So that's my initial thought, just on just very simple reference electrode for glycine based systems. So that's my thought. You asked for my thought, and I now have a thought.
I've not used glycine either, but I'm just looking at its chemical structure. It's
Yeah.
tremendously soluble in water, so my guess is that you're using it in an aqueous system if you're using it at all. It has a carboxylic acid group and a nitrogen, and that's what an amino acid is effectively, I believe.
Yep.
Just sort of definitionally, which means it's as the name suggests, it's acid. It's probably very mildly acidic, which would lead me to believe that you would probably migrate towards a more acid type reference electrode, which would be something like mercury sulfate. Assuming sulfate and whatever the anion of glycine is, what's the name of the sort of H dissociated anion of is it just glycine or
you know what I mean? Like yeah. There's right. So there's the proton, and then there's the I don't know, glycinate anion.
Yeah, whatever it is.
Or
anyway,
I don't know.
The point is, if that is relatively harmless in terms of its likely lack of chemical interaction with something like sulfate's pretty benign and innocuous as well. So just given the acidic nature of an acid, right? Even a weak acid, you're going to probably want to migrate a little more towards something like that. In particular, either use a double junction or a salt bridge if you're going to use something like silver chloride or calomel, because again, making some assumptions here, but in a lot of situations, and perhaps one like this, you might want to avoid chloride contamination. So I would make the assumption that one of the reference electrodes that has chloride in its outer fill solution might be something you would want to avoid. But that's just, again, also somewhat of an educated guess, if you would call it anything, because I also have not worked with glycine.
Yeah. He has just a follow up because he has a concern about WRT ions. I don't
with
know
respect to.
Oh, with respect to ions.
Some concerns with respect to.
I'm like
everything's an acronym, right?
Everything's an acronym. Like, what ion is WRT?
It's the Warburg really
tiny ion. Yeah, that one.
I know. We see so many acronyms, and it gets into our head. I feel you.
Warburg really tiny ion.
That's a new one right there.
That's a new one.
Warburg really tiny ions. That's phenomenal.
So it looks like a ton of questions just came in.
Let's get to it.
We'll get to them. So we have one from Muhammad. Can you please explain the difference between Warburg short and Warburg open? Please explain it with the example of copper corrosion process. Thank you.
Well, that's awfully specific.
Yeah. I mean, maybe we just start with, I know you have I
have slides.
You have slides on Warburg short versus Warburg open.
Let me get some slides out. I'm not sure.
It might not be related to copper corrosion, but it'll still be helpful.
I can try to relate it to copper corrosion, but to be honest, no promises, because that's oddly specific. Let me get, nope, that's not the one. Wrong one. This is the one. There it is. Okay. Let me pull this up for you. Let me get to the slides. All right. Warburg, was it Warburg? What is it? Warburg short and Warburg open?
Yeah.
So both finite Warburgs. Okay.
Okay.
Get to that part. All right. So I'll just
Yeah.
why don't I just go through that part of the webinar for you, I suppose. Let me get presenter. Share the presentation, this whole rigmarole here. Window. Okay. Let me know that I'm sharing is it sharing the presentation?
Yes.
Okay,
Yeah.
perfect. So Warburg is an element that defines diffusion. Okay. I'm jumping, since your question was asking the difference between Warburg short and open, the premise here is that you understand that is a finite, those are both finite length compared to semi-infinite. I'm just briefly explain that for anybody who isn't sure what we're talking about here. But Warburg, typically, as you may be most aware of it, is this W element, which is typically like a 45-degree line at low frequency on your Nyquist plot. That describes diffusion through a semi-infinite plane on the surface of your electrode. Finite Warburg elements describe that kind of diffusional effect, but the diffusion layer thickness is set or finite, not infinite anymore. Okay, there are two types, short and open, sometimes called absorbing. There's other sorts of names. I'll just call them short and open for the purposes of your question as well. Basically, it describes there's diffusion, there's sort of random motion, what have you, in the bulk of your solution, but the diffusion is you call it through an interface or through this diffusion layer of a set thickness. Okay, an example of this would be something like a gas diffusion layer. So again, you've asked for copper. I'm not giving you copper, but I'll try my best to kind of describe that maybe after I've defined each of them, how perhaps that would relate to copper corrosion. Although I'll be honest, I don't have direct experience with copper corrosion related to which finite Warburg behavior is observed. I don't know for sure, but I'll try to talk through at least what I have here to give you an idea. So for instance, a gas diffusion layer in a fuel cell, for example, consists of a layer of platinum as well as a layer of carbon. The platinum is the catalyst, the carbon is porous. And so what we have is a situation here where gaseous oxygen on the cathode side is flowing. You can think of that as the bulk solution, for instance, whether it's gas or it's liquid. You have bulk oxygen flowing, and then oxygen will eventually reach the backside, in this case, of a piece of carbon paper. Effectively, it's a porous. It's called a gas diffusion layer. That's what it's called, GDL. Okay, and it's a piece of carbon paper that is porous, and so the oxygen flows through the carbon to get to the platinum, and that's where the oxygen reduction reaction happens and your fuel cell produces energy for you. Okay. But in this case, because that carbon paper has a set thickness, it's say 200 microns or something like that. And you can even see here, this is from a paper. I think that they measured it. It's, 120 microns or something thick. It's a measured quantity. It's not semi-infinite. The flow of oxygen in the channel behind the carbon paper is infinite or semi-infinite because there's a lot of it. It's everywhere. But the thickness through which the oxygen is diffusing right next to the catalyst, which is platinum, is a known thickness. And so that is what defines the finite Warburg. I'm going to skip the mathematics of it. That's part of the webinar. I'm skipping that here. If you want that, you can watch one of my webinars. I'm going to try to stick to application as it relates to your question. Graphically, the Warburg short element looks like a Randles element, but it has a 45-degree line at the beginning. So it is sometimes confused for a Randles element by itself. So this looks like two Randles elements, two semicircles. But there's this, I call it a lagging feature. I don't really know any other sort of English word to describe it. It's just kind of the word that comes to my mind. Where you have this, again, it sort of starts at 45 degrees. An infinite Warburg would keep going at 45 degrees, but the finite Warburg curls down. Okay. There's another real example. I'm going to skip it for now and move on to the open. So that was the Warburg short. The Warburg open is also has a called reflecting or a blocked boundary. So these are different other terms for it. I'll be very honest with you. This is a strange circuit element, the Warburg open. It's a strange one to conceptualize. I give webinars and teach this, and I still often find myself struggling to like adequately describe the phenomena of what's occurring, because it is quite similar in theory to things like double layer capacitance, diffusion, things that are already known and different. And in fact, are observable through impedance data as well. The theory of this kind of diffusion, it's observed sometimes in lithium-ion batteries, which is why you can see this particular example. These plots are Nyquist plots from a publication. I think down here you can see from 2017. Effectively, there's lithium ions diffusing through a cathode layer, but the difference is that the boundary is not porous. Like the carbon paper was porous, the oxygen diffuses through it. In this case, it's defined more by a solid boundary as opposed to an accepting open porous boundary. And in this case, the solid boundary is the current collector of your battery electrode, which in the case of a lithium ion battery, on the cathode side is aluminum, and on the anode side it might be copper. So there's your copper, there's copper corrosion. I can try to bring it back to that if possible. The tricky thing here, which you might be thinking, is, yeah, but you just showed it diffusing through the cathode layer. How is that not a Warburg short? And the answer to that is, I don't know. That's not what the data shows. It doesn't show that kind of semicircle, right? You see the again, I'm skipping the mathematics of this. Graphically, it looks similar to the one I just showed you for the Warburg short, but instead of curling down like a semicircle, it just shoots straight up. The proportion of which there's this 45-degree part and there's this straight up and down part depends on the thickness of the diffusion layer and the behavior of it, basically. But what you might notice, and if you're familiar with some impedance circuits and how they show up on Nyquist plots, a straight up and down line is a capacitor. So I just said I'm not exactly sure how this differentiates perfectly well, like physically what's happening between the double layer capacitance, for instance. And it's actually somewhat evident because the behavior of a Warburg open, it basically is a capacitor. It's a straight up and down line after a short 45-degree section. So it's kind of like some, amalgamation or combination of diffusion and capacitance, where the diffusional behavior is taking place through still some set thick diffusion layer. That's not infinite, right? But the key is that there's no porous, the boundary is fixed, and not porous. And again, there's a bit of I'm constantly trying to find the right way to describe the phenomenon, because there's that cathode layer that is porous, if you will, or the lithium's diffusing through it. Maybe that's not the right way to look at it. Of course, it's tricky, but graphically, this is what it looks like. And to a certain degree, my answer as far as, well, how do you explain it better than that, is that we just see data that looks like this, right? Like when we see this kind of phenomenon, this is mathematically the circuit element that we can use to describe it. Okay. So those are the differences between short and open, Warburg, graphically, what they look like, a little bit of the background of what they mean in a couple of examples. As it relates specifically to copper corrosion, honestly, again, that's tricky. Your data would probably be an indication as to which of those processes, Warburg open or Warburg short, if either is happening. Your data will tell you which is happening, right? Because the good thing about those two different finite Warburg elements is that they are graphically very distinct. You know when you have one or the other. If it curls down like a semicircle, it's a Warburg short. If it shoots straight up, it's a Warburg open. And then you can kind of use your knowledge about what's happening with the copper corrosion process, for instance, to make an inference. So, for example, if it does shoot straight up, my assumption would be that there's a solid backing of copper metal that's not porous, right? It's like solid metal. And so that's your blocked boundary, if you will. But maybe there's a corrosion layer similar to that cathode layer I showed. And maybe that's where the diffusion layer exists, the diffusion of um, whatever material oxide is causing the rust, basically, right, or the corrosion, something of that nature. Whereas I suppose, again, if you have a Warburg short and it's curling like a semicircle, then perhaps there's a lot. Sometimes what you'll have is like you have with steel and with corrosion metals, you'll get like a passivation layer on the surface, and that may be something that is fixed depending on the experimental condition, and so that might be a fixed length on the surface of your electrode. So that would describe the finite, but it's again, what's the difference between that and the rust layer? There's some ambiguity here, but maybe you'd call that porous, the diffusion layer, and that's what gives you that kind of response. So something like that would be my best, I don't know, educated guess again, I guess, at describing this process as it relates to carbon, copper, but that's the best that I can do. And hopefully that gives you at least an overview of those two types of Warburg elements.
All right, very good. We have a question from Mohammed. What could be the possible reasons if, while performing the RDE experiment, one observes decrease in the current plateau with increasing RPM? So I think we would need to know a little bit more, like specifically about the system. So what I think, and Mohammed, please kind of correct me about what you're referring to. I think am I
Yeah, you're
sharing?
good. You're
All
good.
right, let me.
I'll hide the question if you.
Yeah, just give it some space. So in an RDE experiment, typically, so you have your you have voltage, you have current, and if you are doing, say, and let's say this is 0, you can have systems where, if you're doing a reduction reaction, you may have something that's like this at one like RPM, actually, or at one rotation rate. And then if you had like another color, for example, as you go to faster and faster rotation rates, you may have something that goes like this. And then if you go to a different color, you go here, it goes like this. And so each of these is increasing rotation rate. Sometimes we use like a W or omega to indicate rotation rate. So the rotation rate's increasing as we go down, but the current that we're getting is decreasing. This is the normal response that we'd get to, say, a reduction reaction where you have, say, some oxidized species plus an electron to give you the reduced species. So if you have a reduction and it's at a negative potential, your current will decrease as the rotation rate increases. Now, granted, Mohammed, let's see. So yeah, give me some details. So Mohammed's saying it's RDE experiment of processes like alcohol electrooxidation. Okay. So you're doing an oxidation reaction, not a reduction reaction. So in this case, we would probably reverse this. So actually, let me kind of delete some of these things. So what your experiment? Okay, why did this not? Okay, let's just start over. So what I'm gathering then is you're doing something like this. Again, this is like 0, and then as you sweep, you reach an oxidation potential, and then you get something like that. And then when you're when you're increasing the rotation rate, you should be getting something that looks a little bit like this, right? This would be like the normal response. You'd get an increase in current. Sorry, I just bumped into my my cup. My mouse bumped into the cup, and you should be getting something like this. And this is just like as the rotation rate increases, your current increases. Now, you are suggesting that for this oxidation reaction, which is the following, it's red is going to OX plus an electron because it's some alcohol oxidation, that this current value is actually going down. So let me just see if he has like kind of a response just to figure out what exactly is happening in the system, because I've definitely had cases or have seen cases where the current doesn't increase as high as we anticipate or as we expect. And so if you were to look at the square root of the scan rate as a function of so this is u to the 1/2. I think it's yeah, just 1/2 versus plateau current. So this would be like plateau current. You should get like a straight line in accordance with the Levitch equation. And sometimes at the higher scan rates, you start to see some deviation, which is to say that you don't get as much current as you continue to increase the rotation rate. So I'm hoping if you want to clarify if that is what you're observing or if that's not what you're observing, Mohammed. But you're asking like, but why would you start to see this decrease or not increase as high with increasing rotation rates? It could be a lot of things. You could be dealing with the, in a way, maybe even the kinetics of the system. Sometimes there's like solution resistance that starts to play a role. A lot of non-idealities, usually with an experimental setup. I don't know enough about the alcohol oxidation reaction that you're running and whether or not there may be some kinetic factors, because you have a mass transport limitation, but are you running into a kinetic limitation as you increase the voltage to higher and higher rates? So I think I need to know a little bit more about it, but this is what I'm understanding of your system. Is that what would be very strange though is if as you increase the rate, you're actually getting something that goes like this. It's actually decreasing as the rotation rate increases. That I think is a very odd behavior. And if it's anything, I would say for an oxidation of an alcohol, you may be coating something on the electrode surface, because that does not seem normal. If that was what you were observing.
So I can speak a little to this. It's kind of like that. It's not exactly a coating. Alcohol oxidation is a bit of a weird process. For instance, very often, share this one. Yep. So alcohol electrooxidation doesn't often behave the way a lot of others do. So when you do a CV on electrooxidation of whatever, you might scan up and get a peak and then scan back and get this kind of peak. Oxidation of alcohols often gives you something that looks like this. You scan up, and then when you scan back, you get another oxidation peak.
Oh,
It's
interesting.
very weird. You get two oxidation peaks, you get no reduction peak. Not all the time. Sometimes people do, but not all the time do people do rotating tests with this. It doesn't really behave exactly the same, right? In general, the oxidation of alcohol is not extremely straightforward. It's not a one electron process. There's two different pathways. You can get aldehydes or carbon dioxide, and depending on the catalyst you're using and the complexity of the alcohol, there's multiple steps and multiple electrons involved. And so it's kind of what you were talking about in a more general sense, where the the process, like you're assuming that it would follow Levitch behavior, but it does not, right? It doesn't exactly follow that. And so rotating faster is not a guarantee that you're going to get an increasing, diffusion limitation. You might not even get a diffusion limitation at all. It might still make a peak, in fact. So it just doesn't behave quite the same as oxygen reduction, or just, I don't know, whatever other sort of simple redox, and that's always something to kind of keep in mind in general. I guess we'll move on here in just a second, because I know there's a lot of questions, but in general, it's important to keep in mind that for rotating experiments, a lot of the time, the assumptions built into Levitch, Kentucky-Levitch, Tafel, all these kinds of analyses are one electron irreversible kinetics or something like that, right? Like those are the assumptions built into the use of those equations and the behavior you want to observe. And that just isn't the case for everything. Now, we often make like oxygen reduction reaction is a 4-electron process. We typically use the excuse that one of those electron transfer steps is the fastest, the rest are really, is the slowest, the rest are really fast. So we can just assume it's a one-step thing. It's, whether that's perfectly accurate or not, there's people arguing about it still. The point is that not everything can be assumed to behave this way. And so when you observe behavior, it might be something related to your experimental parameters. You need to iterate, trial and error, try to, I don't know, check your experimental parameters, check the condition of your electrodes, that they're properly polished and properly, all that kind of normal stuff. But it also might be that this is not a system that really behaves and follows Levitch behavior or Kentucky-Levitch behavior or whatever. It doesn't fit under those assumptions, right? That's like I say almost every week when these questions of Tafel come up. It's like, you can't make a Tafel plot if it's not all kinetic data. And people make Tafel plots all the time, and then they wonder why their slope was this or that. And it's like, because you shouldn't have made a Tafel plot in the first place. So in your case, an answer might be you perhaps ought not to. It's not that you shouldn't rotate. It's just that you shouldn't expect the same type of RDE data that you might from something like oxygen reduction reaction when you're studying something like electrooxidation of alcohol, because it doesn't behave exactly the same way.
Okay. Yeah, I didn't know anything about all the complexities of
it's weird. It's weird. I did a little bit when I was in graduate school. Alcohol oxidation is a weird animal. You don't see anything else that gives you an oxidation peak when you're scanning negatively.
Yeah.
I don't know there's anything else that really behaves that way. And you'd never get a reduction peak. And it's like, it's one thing to have an irreversible reaction where you get an oxidation and then nothing.
Yeah.
But another full, and sometimes the reverse peak is bigger than the forward peak.
Oh, that's interesting.
And it doesn't show, it's not the same potential.
Yeah.
And it's like, again, it's intermediates that are formed that are then oxidized again.
Yes.
And why it goes up, it's weird. It's really, it's an odd process. It's one of those that like the hysteresis we've talked about a couple weeks ago. Someone asked about why is there hysteresis in on a battery, GCD. Whatever.
Yeah.
And there's a lot of just theories, and no one's like 100% sure, but it's like mechanical strain or I don't know, something's happening. It's
the
like
battery's under stress.
Yeah, it's under stress. It's like, it's really, it needs to like take a vacation, relax. So anyway, to a certain extent, there's a lot of these odd phenomena that we try to explain as best we can. That's our job. We're scientists. Yeah. But the reality is that we don't always 100% know, and not everything behaves according to the assumptions built into some of these expressions or equations, I guess.
See, the next question from Lawrence, and we'll try to get through these soon. Let's see. How do I correctly select the scan rate for the sweep for LSV? What would this depend on? Or what changes if this is changed? Or what changes if this is changed? Thanks. So the choice of scan rate. So first off, you don't have to just choose one scan rate. You can actually do multiple scan rates for an LSV study. I have found that most of the time, people actually will do some slow scans as low as 5 millivolts a second, and then all the way to say 1 volt per second. And And these are for studies where you're looking at, say, the peak current for an oxidation reduction reaction, or you're looking at the increasing background current for double layer capacitance. So 100 millivolts per second is kind of the standard rate that people look at, or the standard rate that the first time you do an experiment, that might be the rate that you choose. But you may change the rate due to several factors. Sometimes there may be a kinetic thing that you're interested in looking at. Maybe uh, some species need to be formed, and if you scan too quickly, it takes too long, or there's not enough time for a certain species to be generated. Also, background current increases linearly with the scan rate, but for a redox process that's diffusion limited, it tends to have a square root dependence on the scan rate, which means that your background current tends to increase a lot faster than your signal current, your analyte current. So sometimes that makes you want to do a slower scan rate for your experiments. But slower scan rates also take longer. So there are several factors for choosing and using different scan rates. Another one, if you're looking at like an EC reaction, an electron transfer step followed by a chemical step, if you want to probe the speed of the chemical step, you can increase the scan rate, because if the chemical step, if the reduced, let's say you're reducing something, if that reduced species reacts with something in the solution, if you scan very quickly, there's less time for that reduced species to react, and your voltammogram will actually change. So there are many, many reasons why you would change the scan rate. It's just another tool that you have. And unfortunately, without any more information, I couldn't tell you more about why choose one scan rate versus another. But as you do eChem, you may find that, this data looks kind of weird. Let's slow the scan rate down, or we can go a little bit faster. It'll give us, we want to get these experiments done faster or something like that. So it always depends on the situation, I would say. But Lawrence, let us know if you have any further questions about the LSV scan rate.
He had a follow-up.
Oh, he
I'll
did
just
have a
mention because
follow-up.
I just noticed it here. He said,
No, okay.
recommended to do, I guess, 0.1 to 10 millivolts per second, as that'll be the best for kinetic studies, and that is really slow. Yeah, so if you are trying to do kinetic studies, like make Tafel plots and everything like that, you are going to want to scan very, very slowly. In the case that you can, as much as possible, assume that the current data from a sweep is only related to kinetics, you would have to scan very slowly for that.
Mm-hmm.
As you scan faster, the impact of the double layer becomes bigger. The Randles-Septric equation, I think, is describes that. Or no, what's
just the current's equal to the capacitance times the scan rate.
So just a simple So basically, as current goes up, as the scan rate goes up, the capacitance also goes up. So there's a direct relationship there. So basically, as you minimize the scan rate, you minimize the double layer capacitance, which is a non-Faradaic, non-kinetic contribution to the current. And basically, it's like the window, the window between the positive and negative. I know you're doing LSV, not CV, but still, the baseline current, if you will, diminishes as you scan slower and slower. So yes, 0.1 millivolts per second is really slow. It's also about the scan rate that people use for corrosion studies. And because in corrosion studies, you're trying to determine kinetic parameters, basically, quite often, okay, in a corrosion study. And so you have to scan very, very slowly to be as sure as you can that the current data is related to kinetics. So yes, if you're trying to do kinetic studies, you do want to scan quite slowly.
Okay, and then let's see. So, all right, making sure we're back. Chica asks, "Hi, I was wondering why your knowledge base, referring to I think the Pine Research knowledge base,
I have no base of knowledge at all. So thank you.
Specifies the working temperature range for the RDE tip made from PTFE should be between 10 to 25 degrees Celsius, as stated here. And then there's a follow-up from Chico, which says, I ask because there are a lot of experiments out there using your products to do RDE kinetic measurements up to 50 degrees Celsius. So I would hope or imagine that people who are doing those RDE kinetic experiments at 50 degrees Celsius are using an electrode that has a peak polyether ether ketone shroud around the electrode instead of a PTFE shroud. I think there might be some possible issues for those who have who are using PTFE as the shroud material. What tends to happen is the PTFE shroud will expand and contract quite a bit when you temperature cycle it. So it's just the thermal expansion coefficient of PTFE, and our electrodes for a rotating disc are kind of the core of the electrode doesn't move. It's quite stable, but when you have an expanding and contracting PTFE shroud from temperature dependent studies, you can form leaks. So we have some electrodes that are in PTFE shrouds that are stationary electrodes, and they don't have the core inside, and so the electrode material can expand and contract together, and so you don't have a leak. But when you have certain RDE core electrodes that are very solid and don't move or don't change, they don't heat up and expand and contract with the Teflon, you can form leaks. So that's the reason why we recommend you only use a PTFE shrouded electrode between 10 and 25 degrees Celsius.
And I'll just add to that, which exactly everything you said, but for those who sometimes are confused by that because they say, oh, well, PTFE doesn't melt, or it starts to basically fall apart at about 200C, 210C, in that range.
Mm-hmm.
You know, actually can be quite dangerous if you go that temperature, because it's tetrafluoroethylene. You get like fluorocarbon.
Probably.
Yeah, you can get outgassing of pretty dangerous stuff, actually. So anyway, just as a side note, if you're heating Teflon in an oven or something, please be careful.
Yeah.
It can be dangerous. The point of this is that 50C is well below that point. So it's not a danger from like the PTFE melts or anything, but it's exactly what Alex said, is that because it's the softness of it does not take a lot of temperature or heat to cause PTFE to slightly start to move. And the real danger is that even at 50C, you can have it start to move ever so slightly, and then the seal can get compromised. And if the seal is compromised, it can damage the electrode beyond repair. That's frankly the case. We test all of our electrodes to be leak-free as best we can. We manufacture them. It's a very complicated process to make one of these RDEs. And the peak is needed because peak is much harder. It doesn't move as much at temperatures. You can go up to 80C with peak. Teflon just doesn't have that luxury, unfortunately. So yeah, I believe that people are using it, and perhaps they're getting away with it in as much as you can get away with it, but it's not a recommendation. Unfortunately, we can't recommend people use our PTFE shrouds at a higher temperature. It's very likely that the seal will be compromised, and if you get leakage, your data will be poor. So.
We have a question from Vivek. Vivek has a few questions, actually. How to calculate ion and electronic conductivity of an electrolyte. Sorry. And then he specifies just a little bit later, he's interested in solid electrolytes. And kind of following up a little bit, he wants to know a little bit about can you explore the life cycle of an electrode via galvanostatic charge discharge experiments. So I actually don't know enough about how to really calculate ionic and electronic conductivity of a solid electrolyte, what kind of experiments you want to do. I know that some people calculate things like ionic strength, but that's different than the conductivity. I think there are some, and whenever someone asks for a conductivity experiment, I usually recommend doing impedance spectroscopy, figuring out what the resistance is, and then just taking 1 over the resistance to get the conductivity for that species. But I don't know if you know anything else
Yeah,
or more about
I
it.
have a little bit of a thing I've shared before. I'll share it again. It's related to a product that we sell. Again, I'm not trying to focus incessantly on marketing my company's products, but since you asked, I'll share this. Sorry, I'm just getting the material into like a Word document I can kind of share here. So there's a cell. This isn't exactly necessarily like a solid electrolyte thing, but it's the fundamentals are similar. So for example, we sell a device that looks like this. So you have this hardware in the middle, right? And you have two pieces of glassware, and you have 2 luggin capillaries that basically meet in the middle. Okay. You put 2 drive electrodes, 2 reference electrodes. So it's a 4-point experiment. Effectively in the middle, you have a distance between the 2 luggin capillaries. You have some membrane. Okay. And this is where, again, solid or this requires solution. So it's not exactly the same, but there might be some analogous, I don't know, situation here. You either run impedance, like Alex said, or a short LSV at a very slow scan rate, like I was talking about before. You're assuming you're trying to minimize the impact of capacitance. Okay, and a short LSV experiment will have hopefully a straight line, and the slope of that line is the resistance, right? V is IR, Ohm's law, right? So effectively, you can get the resistance and conductivity. There might be other, I don't know, ways to calculate it exactly, precisely, but one method of calculation of conductivity is L over RA. Okay, this is actually not what I. This is actually incorrect.
To the minus 1.
It should be Siemens. It's Siemens per centimeter, I think is because R is ohms. Yeah, I had the unit upside down. Anyways, the inverse of ohms is Siemens. So you either sometimes it's described as ohm centimeters or Siemens per centimeter. Those are just inverse of each other. The way that people report it kind of varies, but effectively, resistance is kind of conductivity, just like the inverse of it, right? There's also conductance and then conductivity, and I think that they differ by just that length unit. And so it's a bit tricky, right? So the area of your membrane that you're studying plays a role. The distance between these luggin capillaries is the L. There's ambiguity here because what's the distance in your particular? It's the distance between the sense lines. So for a solid membrane, you might have something like your solid membrane kind of flat on a surface, right? Whether you have maybe it's soaked. A lot of times people will soak it, so it's like soaked in solution because like there just has to be some electrolyte or some ion movement. Maybe the solid electrolyte itself has ion movement, but then you can put like probes just literally touching the surface. So this would be like working sense, and then reference, and then a little ways away you'd have working drive and counter. And so your distance would be this distance. This would be the L basically. What's the surface area? I guess it's the whole. Is it the whole thing? I'm not 100% sure either. I'm kind of explaining as much as I am sort of aware of. This is a way to kind of calculate the conductivity. Now, the tricky thing of this is that this is, to the best of my understanding, conductivity of the membrane, not conductivity of the electrolyte. Those are different things, right? There's And also it says ionic conductivity, not electrical conductivity. Calculation of electrical conductivity is a different thing. And I don't believe it's exactly electrochemical to do that. It's not right. That's
Well,
like that's like a band gap thing. And that's a different, I don't think, this process I'm describing is ionic conductivity. That's, I believe that's what you're getting at when you're doing this kind of a test. Is that right?
yeah, I don't know enough about like, well, it's like in some cases electrons move and in some cases ions move. And usually for my limited knowledge, the place where ions move is different than like if you apply a voltage between two things. So let's say if you had two electrodes and then you had an electrolyte in between them, you're looking at ionic conductivity when you apply a voltage.
Yeah.
But if you had a wire between two electrodes, you're looking at electrical conductivity.
Yes.
The voltage, one promotes an electron moving, one promotes ions from moving, but the technique itself would probably be, or the setup at least would be similar.
So I think that's right. And I think that what I described falls under the first one you said, which is ions moving. So the tricky thing about this, because these are used sometimes like people say conductivity and they don't specify which they're talking about. And the tricky thing, of course, is conductivity in general is describing charge moving.
Right.
And ions or electrons can move charge. So the differentiation between those two is sometimes murky.
Yeah.
The process that I just described, which is used electrochemically very often, it is usually descriptive of ion conductivity in a membrane. It looks like Vivek has a bit of a follow-up. I'm using pellets of solid electrolyte. The parallel surfaces were polished via silver epoxy compound.
Pellets?
Okay, I'm not sure if that's a question or just a comment. It looks more like a
pellet
comment.
was polished with a silver epoxy compound. That polished. So whenever I hear polished, I think about mechanical abrading, I believe is the term, to like physically remove parts of something.
Is it abrasing or
abrading? Abrading.
I think it's abrading.
It's abrazing.
I think you're right. I think it's abrading.
Abrading. I use
abrading. You're right. It's
abrading.
But the process is abrasion.
Yeah, it's
That's
abrasion. Yeah.
Why do English is the worst language?
It is the worst language.
It really is.
Oh god, I heard this comedian who was just like, English is so weird. It's like certain things make so much sense, like present and past tense. It's like looked, sleep, slept, kind of weird. But then like the past tense of go is went. It's like totally different. It's
Why?
Not goed or
I goed.
Yeah. I went somewhere. I'm like,
have you ever heard little kids talk? They say goed because it makes sense. It should be goed.
It should be goed.
And you have to be like, no, that's not it. And I don't know why, but that's just what it is.
So we're talking about abrasion, and we're just talking about like a simple word. But when you say polish via a silver epoxy compound, usually epoxy means like you're connecting two things together. So I'm a little confused about that. Maybe you're just connecting the pellet with like silver epoxy, so you put two wires across it. Something like that.
Yeah, that could be a way to make that electrical connection.
Yeah. So but yeah, you could, I mean, and actually, so one thing between like electrical conductivity and ionic conductivity is just like the voltage required is really the main thing that's going to be different depending on the system. So, but you're right, like you're just moving charge in either one, and really you're using an electrical device to measure the conductivity, ionic or electric. It's the same. It's like the same device. We measure the charge that passes across a thing or the current that passes across a meter, and whether that that voltage movement or whatever to make a measurement is coming from an electron, electrical conductivity, or coming from an ionic conductivity. It's not always super clear, but hopefully that gives you a little bit to think about. I know we still have a lot of questions.
Plow ahead, right?
Yeah. And so I guess Vivek did have one last question, which was about just measuring, like, can you measure the the life cycle of an electrode. So I think you know that like batteries, you can tell the life cycle of a battery via galvanostatic charge discharge, but an electrode is just like it's just a piece of some conductive material, like a piece of metal. So it's not necessarily like a life cycle per se of an electrode. I mean, stuff can happen to an electrode, and you have to polish it to create a new surface. Um, but I don't know about using galvanostatic charge discharge for measuring the life cycle of an electrode.
If your electrode is something that is charged and discharged, then
Yeah.
yes. If it is just an electrode and you're just studying various redox processes on it, but they're not specifically charge discharge categorically, like in the way that a battery is, then your galvanostatic experiment is not galvanostatic charge discharge. You're just doing chronopotentiometry.
Mhm.
Technically, they are similar, right? Galvanostatic charge discharge is the description of an experiment where you apply a positive current to charge something for some period of time, and then you apply a negative current to discharge it for a period of time. That is also chronopotentiometry. Chronopotentiometry is chrono, time, potentio, potential, metry, measuring. Chronopotentiometry is the measurement of potential over time when you are setting the current. It's a galvanostatic method. But charge and discharge is a very specific terminology associated with a battery or a capacitor or something of that nature that can be charged or discharged. It's a fundamental changing of its state as you apply a current for an extended period of time. Not everything behaves that way. Not everything that is described as an electrode can be described as having a charge or discharge process. Sometimes it just undergoes some redox processes.
Mhm.
So I just want to make that clarification.
Yeah.
So if your electrode is like an anode or a cathode or a material that can be charged or discharged in one of those kinds of devices, then yes, of course, that is the way to just discover the life cycle, how long it will last and how much it degrades over time, etc. Then yes, galvanostatic charge discharge is what you're going to use. But if it's just an electrode in general that performs some redox process, like just glassy carbon and acid, no, you're not going to be able to really determine life cycle by doing galvanostatic charge discharge. There is no charge or discharge. And you would probably want to do something like cyclical voltammetry for a while to discover its stability or something of that nature.
So we have a question from Gary, and he had one that was retracted. So I'm gonna skip that one. But but thank you for being a member of our YouTube channel. If you want us to go back to your other question, we certainly can. But Gary asks, what information can be gathered from EIS data apart from conductivity, resistivity of electrodes? Which software would you recommend for EIS data fitting? And Gary also asks another question, somewhat, we can answer this one as well, but how to measure specific surface area in meters squared per gram of the electrodes experimentally, for example, in the case of porous materials. So I think we'll start by talking about what information can be gathered from EIS data, apart from conductivity and resistivity. Usually, and I think you've indicated that you also do a level of EIS circuit fitting to your EIS data, and usually that circuit fit contains more than just the conductivity and resistivity of your system. Um, there are things like solution resistance. There's double layer capacitance. There is charge transfer resistance, and depending on your system, there can be a variety of different what we use circuit elements to represent physical phenomenon. And so it isn't just the conductivity and resistivity of electrodes, but also anything that has an interface and a process that takes time, time to charge and time to discharge, you can learn more information about that by doing EIS. And so I don't know if that makes a whole lot of sense, but for your recommendation, which software would you recommend for EIS data fitting? our software. We have our own software.
I was worried you were going to say something else.
I
All
was
right,
just
good.
like, you gotta get the software from the other.
Hey, if you ask and you shall receive. Right?
Yeah. So our aftermath software, which is used to control our potentiostats, it's a data organizer. Specifically, Aftermath Live is an online streaming platform that we have that you can upload data, you can upload EIS data, and you can do circuit simulation and circuit fitting. So you would
I don't know if
create.
circuit fitting is part of
Oh, it's not part of Aftermath
I think
Live.
we're going to do that eventually.
Mhm.
For now, if you want circuit fitting specifically, the electrochemical simulation is available on Aftermath Live, but circuit fitting
Mhm.
is we sell licenses for that.
Oh, okay.
It's a an application. You know, we can get you the files for that. I don't know actually, to be honest. You might be
Okay.
able to do circuit
And
fitting. I don't
yeah,
think it's part of
we
Aftermath
haven't
Live.
tried it yet. I guess we
Yeah,
should just
yeah.
try it. We've been making a lot of updates to our software, both online and installed versions on our computer. That
This is our software, by the way. Here it is.
yes.
So,
Oh,
for
hi.
instance, for doing circuit fitting, you can see the Bodhi and the Nyquist plots at once. You get to pick your circuit. I know you probably can't see the circuit thing because I'm not sharing this part, but you pick the
Yeah, that's
circuit
okay.
that you want to fit, and then you can adjust the parameters and see how they adjust in real time, how they change the fit. It's a pretty nice interface.
Yeah.
And then it can calculate the optimal parameters for you. So
Mhm.
that's just a small little snippet for you.
Yeah. Yeah. And that's some of the information. And then to your other question, how to measure specific surface area in meters squared per gram of of the electrodes experimentally. For example, so I have heard about many different areas of measuring the surface area. I had a long conversation with somebody about this. There are several different methods. One method that somebody mentioned to me was actually using capacitance. So if you use EIS and you determine the double layer capacitance of your material, full electrode area exposed to solution, you can, depending on what it is in the system, you can look up a factor that relates the capacitance, the current associate, the capacitance value with the area. So it's like you get capacitors per meter squared or something, and you're able to determine the area of your electrode that way. So these are things where sometimes you have to like look up the value, and then it's always like, well, how'd they get that value? Where did that come from? The other option thing to think about is to use the equation for capacitance, which where the capacitance, no, not the equation for capacitance as it relates to um distance. Oh, okay, capacitor, not capacitance. I need capacitor formula. But a capacitor formula, let's see.
It's like dielectric constant times the area over the distance or something like that.
Yeah.
Something like
Right.
that.
So yes. So the capacitance is equal to the dielectric constant times the area of the electrode divided by the distance. So the distance. So those are things that are kind of complex because the distance of your capacitor is like a nanometer at most, probably like several angstroms because it's for the double layer capacitance, and then the dielectric, which is known as like epsilon, can sometimes be a kind of a very random number. Some people just use water if they're using water as the thing that your porous electrode is in. So they use like 40 or something like that. And so they come up with some of these numbers to actually determine the area, and then if you know the mass of your electrode, then you can determine the specific surface area of your electrode. So that's like a way that some people have gone about measuring the specific surface area.
The other way that people measure the surface area, though, is not electrochemical.
Oh yeah,
So
BET.
BET, yeah. So
Yeah.
Brunauer, Emmett, Teller, I think was the name of it.
Mhm.
Is an apparatus. It's a piece of equipment. It's a big, probably multi-$100,000 piece of equipment that you would have to have in your research facility, probably. It effectively measures that specific area per gram or per mass or whatever by it cools it down, cools your sample down, and then sends nitrogen gas through, which absorbs to your surface, and then it releases the nitrogen gas and it measures the release of nitrogen. It's called an N2. It's a nitrogen absorption isotherm. Anyway, that is not electrochemical at all. It's just a physical characterization technique. It's something that's commonly done with like powder electrodes to get a specific area. And so that is specifically the unit that you get from a BET analysis when you do it. It takes usually a couple hours to get. I did it when I was in graduate school, and you get the specific surface area. So BET, look that into that as well if you want a pretty rigorous, I guess, expensive piece of equipment. But if you're at a location or a research laboratory or facility that has a BET machine apparatus or whatever, that is another way to get it, not electrochemically, I suppose.
Yeah. All right. So the next question going down the list is from IITM Diaries. How to decide the potential window for CV or any charge discharge profile diagram? On what basis we decide it? That's a very good question. I think generally speaking, so potential window and for CV, and then of course if you're doing, I guess, a galvanostatic charge discharge experiment, the general idea, and let me, I guess, just share my screen, is and at least whenever I'm doing these kinds of things, and I never know what the potential window is. So if I have voltage, I have current. I'm just gonna make this very simple. Anytime I have this kind of flat region where nothing is happening, that is what I define as like the usable voltage range where nothing else is going on. And when I see stuff like this, I'll use red so that it's easier to see. But every time I see stuff that's like this, where I have a lot of current going down in for my voltage, and then when I'm at a higher voltage, I have my current going up a lot. It's much harder to try to see any like features or peaks in either of these areas. They'll be convoluted by current that's moving. So even if you're doing the charge discharge experiment, you'll commonly observe like, oh, your current or your voltage or whatever is starting to increase or change quite a bit. That's what we kind of define as the limits of the potential window. And so if you're studying a redox species or a redox process, it's much easier to see something if it's inside of your potential window. But if it's here, it's very hard to see because it's convoluted with all this other current. So one of the best ways I know how to find one of these things is just to do some voltammograms in your electrolyte system, and then just see how far you can go without seeing a huge increase or a huge decrease in the current. And keep in mind, when I first started doing electrochemistry, I wasn't paying attention to the y-axis. Sometimes it can look like the current is going up really, really high, but you only have maybe a few microamps of current. Sometimes, if you're expecting something that's in the, milliamps, then okay, well, maybe you should go further and further up. Maybe your range is actually a lot higher than you think it is. So that's the kind of simple and short answer for how to determine the voltage range that you want to work in and the potential window. Let's go down the list. We have Somya. Somya is asking how the rotation rate can affect the RRDE collection efficiency. Should it be independent ideally?
Yep.
Yes. Yeah, they should be independent.
But it's not always.
Sometimes. Yeah.
Yeah. How it impacts it is that sometimes I think this happens. I suppose it could go either direction, but my observation tends to be in some situations, if you calculate the collection efficiency at really fast rotation rates, it's lower than it should be. And that's just because the hydrodynamic behavior isn't ideal anymore for one reason or another. It might, as you rotate really, really fast, you start to push the rotation rate higher and higher. You might get cavitation, you might get eddies and odd flow patterns that are not behaving ideally anymore. The assumptions associated with hydrodynamic flow at a rotating flat disc electrode and disc and ring and everything start to break down as you rotate really, really fast. You can get cavitation, you can get all these kinds of effects. And so this is why it's also very smart to measure it experimentally over a range of RPMs, and you don't want to go too fast often. And actually, in a kind of an interesting way, I guess I would say, is one sort of empirical way you can employ to determine, other than for example, our rotating disc electrodes, we have, stated safety limits for how fast you should rotate and that kind of thing. But just in a general explanation, if you're trying to figure out how fast should I rotate before the, behavior isn't behaving properly anymore, you can kind of measure the empirical collection efficiency at every RPM. And you might find that at, 2,800 RPM, it starts looking like the number's not accurate anymore.
Yeah.
So perhaps that's, but I should go 2,500, no faster. I'm just, thinking very generally with these numbers. So that can be one way to sort of empirically or experimentally determine, basically like a maximum practical rotation rate for your specific setup and cell, where the hydrodynamic flow patterns are still ideal, for example.
Yeah. Yeah, absolutely. All right, moving on, getting through some of these. This is good. We have a question from Noreen Khan. In Tafel analysis from LSV, which part of the Tafel plot should be taken for determination of Tafel slope? Although LSV is not good for determination of Tafel slope, but in the literature it is reported. So I guess if we just kind of draw a really simple Tafel plot, or at least what I see in the literature or something of Tafel slopes. So let's see. So I'm just gonna do. Actually, no. They always have they always draw this kind of like so. So this is the x-axis is in the middle, and then let's see. We have voltage or over potential. So it's eta.
That's on the y-axis.
Eta is on the y-axis.
Mm-hmm.
And then you have
it depends. So practically for what people are doing,
log 10.
Yeah, you can do either way. Actually, what you're probably going to draw is more like the textbook sort of Butler-Volmer kind of whatever. That's fine. You can draw it this way.
Yeah, so I was going to draw a little bit like this, and then it kind of. I know it's not perfect, but it curves a little bit here,
mm-hmm.
and then it's straight. And this is like log of current.
Yeah.
Log I. So what I usually I think recommend is you want the quote linear portion of it. It should always be linear, and that linear portion, I believe, some people say it's like maybe 100 millivolts or so, maybe more, at least 100 millivolts from over potential, because generally speaking, the in the Tafel analysis and just the Butler-Volmer equation, you know, your current is equal to some constants. It's just like Fa, um, exchange current density. But then you have this like concentration of like your oxidized species, and then you have the minus concentration of your reduced species, and then you have your whole like e to the stuff
Yeah.
here, e to the stuff,
E to the stuff.
e to the stuff. Like it's like NF over RT minus
Yeah.
beta and all that stuff. So basically, what you're trying to do is there's over potential here is both in this. There's an alpha somewhere, and what you're trying to do is at around 100 millivolts or so is when e to this power makes one of these much bigger than the other one. That's the key. You just want to make sure that this guy is the dominant factor, or this one is the dominant one. Now, this, of course, this is Butler-Volmer, so it assumes that you have like an equal concentration of both species. If you know that you just have one of your oxidized or reduced species in solution, then you may be able to get away with like a lower over potential. You can maybe start here, but at least the way the equations and stuff work right now is, you want to have an over potential where one factor is dominating one half of the equation, one half of your signal, and the other one's dominating the other half, like the anodic or the cathodic portion. And so I kind of tried to draw these curved because it's not linear in this short region here. So that's the general rule of thumb. And this is for like, LSV. So, people get their voltage current curves, they do stuff. And but then it needs to be converted into this for you to do the Tafel analysis. So just keep that in mind when trying to use the Tafel analysis and determine the Tafel slope. Tafel slope should be used from this portion of the data, generally speaking. I hope that that answered your question, Noreen. And let me just see if there was any. Okay, no, doesn't look like there was a follow-up.
And as a repeat from we talked about a little bit earlier, you are correct that LSV is often not really ideal to use for determination of Tafel slope, but it's used in the literature a lot. That's correct. A lot of people are inappropriately using LSV for Tafel analysis. One of the ways, as we said earlier, you can try to minimize that error is to scan very slowly. So if you're using LSV to determine Tafel behavior, it needs to be kinetic only. And so one of the ways to try to get mostly kinetic information is to scan very slowly, like 1 millivolt per second or slower. You minimize capacitive non-Faraday effects, and it's, let's just say, roughly kinetic information. So that would be my recommendation. In addition to what Alex said, getting a big enough over potential that it's mostly irreversible, and then you can make the assumption of Tafel analysis.
Next question is from Fernando. Fernando asks, I have a screen printed, I think this is a screen printed electrode modeled by a Randles cell with a Warburg element. After electropolymerizing a compound on it and characterizing it by EIS from 1 megahertz to 0.1 megahertz, I only see half a semicircle. Is it valid to discuss? And I think when you say valid to discuss, you just mean ask why you only see half a semicircle. I'll just take a stab at it. I think you might have to go to lower frequencies. Sometimes I've done just regular EIS of just like not even an SPE or something very crazy, but I feel like I only see the completion of the semicircle and Warburg diffusion when I scan, where I'm doing frequencies at very, very low frequency ranges. So, what is that? 100 millihertz. I don't know if you have to go to 1 millihertz to see it. That'll give you a few extra decades of signal. But it's like seeing half of a semicircle. So I don't know if you're gonna actually see a lot more.
Yeah.
If you go to if you collect 2 or 3 more data points. I'm not so sure.
Yeah. If what you're seeing, I'll even be more direct.
Mm-hmm.
If what you're trying to describe is this, if this is the desired circuit, and this is your data, then no, can't use that. You just can't. There's no Warburg behavior here. If you go to lower frequency, as Alex said, and you started to get that, then great. Then you can have your Warburg stuff. But if you have just half a semicircle, it either means you don't have any Warburg behavior, probably, or you haven't gone to a low enough frequency to elucidate it. But if you just have that, now what might happen is you might actually have your semicircle here, and this is actually like Warburg information. It's just so there's interpretation here. But if this is truly just one like part semicircle, then using a Warburg and all this kind of stuff is most likely not accurate. It's not descriptive of what you're seeing in your data. So you would have to either, like you said, go to lower frequency to finish the graph, basically. You could probably fit that with a Randles element, just a Randles, but no, there's no Warburg going on there. You're not observing the Warburg behavior there. So
yeah, another thing is what is it, Neil? If your EIS baseline is not doing any electrochemistry, like there's no redox process, there's no diffusion occurring, then that's also going to affect what the Nyquist plot looks like. So make sure you're not just doing EIS at open circuit. You may actually need to be doing EIS at a potential where the chemistry is occurring.
Excellent point. It's one of those questions I get all the time that I still feel baffled about. People don't think about impedance the same way they think about CV or bulk electrolysis. If you're trying to study this particular oxidation reaction that occurs at 500 millivolts and open circuit is 0, why would you do impedance at 0? Do impedance at 500 or 600 or whatever. Like you have to do, if you're trying to study whatever reaction that occurs at X potential, then apply that potential and do impedance at that potential.
Yeah.
Otherwise, you're not studying it. You're just studying open circuit. There's nothing going on. There's no Faraday process. You're not going to get Warburg. You're just going to get capacitance, right? You're not studying. People often don't, like, there's something missing in our brains with impedance. It's
well, the thing that was like, because I made this mistake a lot. The thing that was missing in my brain was I was just like, Neil always says, just like, okay, linear, causal, and stable. But how can my system be stable if I'm applying this big potential? I know I need to do EIS where nothing is happening. That way it's stable. That'll show him. That'll make sure.
You'll show me.
Show him.
You can be stable at an applied potential.
Yes.
Apply it, let it sit for a minute, then it's stable. It's
yes, yeah. I didn't realize that.
Yes. I don't know what it is. I really don't know what it is. There's this odd, like, it's like just odd human behavior. It's so common.
Please don't tell me doing EIS is common.
No, it's not. But if there's anything common about it, it's the fact that like almost everybody's brain works this way. It's like there's a lot, and I get it to a certain extent. Impedance is complicated. The analysis is weird.
Yeah.
You have imaginary numbers and stuff. It's all made up anyway, so whatever. It's just a weird test. It's a hard test, and the analysis is difficult. And there's a lot of parameters like frequencies and amplitudes and all this stuff. I get it. I get that there's a lot to think about. But one of the things that's never thought about for some reason is the set point. People just assume it's like, it's open. You just do it at open circuit. Just apply an amplitude. It's like, why? You wouldn't think about chronoamperometry that way.
Yeah.
You wouldn't be like, I'm going to do chronoamperometry to study oxygen reduction reaction. So I'm just going to apply open circuit potential and see what happens.
Yeah.
It's like nothing happens. No, you're going to apply minus a volt or whatever, so you're reducing oxygen. It's like, of course you would. So why wouldn't you do the same for impedance if you're trying to study something?
Yeah, I know.
I don't know. It's weird. It's weird behavior.
While what we just described might not be the answer to this next question, we do have another EIS question up from Fred. Fred saying, my Nyquist platform is a very small semicircle and then it shoots up, but not with a 45-degree angle, and may look like it's making a second semicircle. Is it Warburg? 20 millivolts is probably the amplitude.
In the dark.
Frequency is put 0 hertz. So he's going from, I guess, slow to fast, but then
not necessarily. Some people report it that way. You
they
should be
report
going
that
fast to slow,
slow.
just to be clear. But typically people report the fast frequency first, just as an indication of the order that you went. You should be going fast to slow most of the time.
His other comment was on another experiment with another material. I even got no semicircle and the curve went up directly, but not linearly. Oh, interesting.
I don't know what went up directly but not linearly means exactly. I'm trying to picture that. To the first question, it might be Warburg. It might also be a second charge transfer process that has a tremendously large resistance associated with it. You can imagine if it's starting a semicircle, but if it's just like, it would continue like in the next county on your plot, like 5 trillion ohms over. It's like the width of that semicircle is associated with the charge transfer. So it's like a really, really kinetically unfavored process, but there's still a process there. That could be what's happening. On the other hand, it could just be there's some drift to your data at the lowest frequencies, and it is Warburg behavior, and the appearance of a semicircular shape is a consequence of sort of drift or noise or something, right? And if you can't easily identify, let's just say, a process that I described in the first thing I said, like there's some other process, for example, maybe another redox process that takes place a few 100 millivolts away from wherever your set point is. And so it's kind of like if you were before a peak, on a CV, right? You're like at the potential before the peak happens. It's still happening, but to a really low extent, right? Like the E0 is 100 millivolts. Even at 50 millivolts or 0 millivolts or whatever, it's still happening, like really minimally, right? Like, but not a ton.
Yeah.
But it still can actually have some of that oxidation happening, for example. So that could be what you're seeing, right? Like it's that semicircle is related to like a process where you're at a low enough potential that it's not very favored, but it's still happening. But if you can't identify, for example, like, well, there's no process happening. Like I know what my electrode is. I know what redox processes are taking place here, and there isn't anything. There's no other, or at least I don't think there is. Then it might be the second thing I said, which is that it might be Warburg and it's just behaving non-ideally or something. My suggestion is do Kramers-Kronig, right? Sometimes with Kramers-Kronig analysis, what you observe is at high to mid frequencies, it fits really nicely, and at low frequencies, it's terrible. If that's what you see, that would be a good indication that, okay, it's just drifting at low frequency. Fine. So my data is mostly good. At the lowest frequencies, it's a little bit unstable. That's normal. It's somewhat normal. It's not ideal. If you can fix it, if you can do the experiment again and get some more stability, that's fine. But one of the answers to that is to say, okay, fine. My lowest frequency, my lowest decade of whatever, is a little drifting. So I'll just smack a Warburg on it, get the fit, and it's got some error. Fine. No, it's okay. It's okay to have a little error in your measurement, right? This is science. There's always error, right? That's an okay thing to do. I mean, if you do Kramers-Kronig and it's just a dumpster fire, you need to throw the data away and try again. But there may be a situation where most of the data is accurate and okay, but at low frequencies, it's a little bit drifting. And so the appearance of what looks like a semicircle is actually just sort of a fake thing. You know what I mean? You can fit it with a Warburg and still get some decent analysis. And again, on the second part, I don't know what you mean.
Not linearly.
I don't know what, I don't know something that just goes straight up, basically, is kind of what it sounds like you're talking about. That's just capacitance and or diffusion. If you just kind of have this like no semicircle, it just goes like straight up. That's a constant phase element or a capacitor, basically. And if it goes straight up and down, it's a capacitor. And if it goes up at a kind of an angle, not exactly 45 degrees, but like if it made like a 80-degree angle with the x-axis, that's basically like non-ideal capacitance. So a constant phase element would be the fit for that, I guess, something of that nature.
Fred is asking,
how to do Kramer's Kronig. So it's for example, in our software, again, not to plug our company over and over again, but the circuit fitting with our software, I'll just sort of show you here.
It's just a button.
It actually isn't. It's actually a lie. It looks like a circuit fit. It's not really a circuit fit, but you have data that whatever. We have there's a button, does Kramer's Kronig, and it just does it. So it looks like a circuit fit like this, right? And so you would basically do the analysis I was talking about. Is you would zoom in, you'd be like, oh, this fits pretty well. Okay, fine. And then maybe at lower frequencies, as I start to go along the Nyquist plot, you see it starts to deviate a little. This one's actually pretty good, for this part. But there's a little bit of deviation here at the mid to low frequency range, and so maybe it's a little bit not perfectly accurate or whatever. But the analysis is usually built into software. You can obviously code it yourself. I have done so with like Excel. You can write a macro to do it. It's a little complicated, but anyway, how to do it mostly is, frankly, in software, built into software. And our software is one of those that can do it that way. So
okay, I think we have a question from Zaki. Asks, what is the difference between a luggin tube and a salt bridge? When is it okay not to use one? For corrosion experiments, what solutions should be used in a bridge/luggin tube?
I think everyone's trying to trigger me today.
I know.
Luggin capillaries and Tafel plots. If someone asks a question about chi-squared, I'm just leaving.
Oh, I was going to mention, it's like, well, how do you know if your Kramer's Kronig is good? Well,
how dare you? I'm going to ask you a question about inductive loops.
I didn't say it, though. I just thought it.
But now you said it.
But now I said, but that's because you were talking about triggering things, and so I just figured I'd mention triggering things.
How about them naming conventions and inductive loops, huh?
Yeah.
Oh man.
So Zaki,
aren't those the same thing? Am I losing it? Is there a difference?
Well, this is how I think.
I thought a bridge tube was just a synonym. Am I wrong?
Well, a salt bridge. I mean, I think they are.
Oh, if you're talking about a salt bridge.
Yeah, I thought, is that not what he asked?
I don't know. Bridge.
Oh, bridge tube. I guess maybe.
I think that's
maybe it's the same thing. So I wouldn't really be drawing much of anything then.
You could draw the difference between a salt bridge and a luggin tube. That would be helpful, because if that's what the question is, it might be. I'm not 100% sure. I think the term bridge tube is used interchangeably with luggin tube, luggin capillary.
Yeah.
But salt bridge is a different thing.
Yeah, salt bridge
than luggin capillary or luggin tube.
Yeah. So like if you have your reference electrode, and it's like here. Sorry. So this is RE, and this is working. A luggin tube is basically, it's a container that it's just kind of pointed glass that has a little tiny entryway right here, right next to the working electrode. Let me just put the counter electrode here this isn't drawn, correctly, but it's just for say. But this is what a luggin tube is. A luggin tube is just a tube that that puts the quote sensing point of the reference electrode very close to the working electrode to minimize the solution resistance, or the IR drop that occurs when you're making a measurement between the working and reference electrode. So that's what a luggin tube is, or a luggin capillary. The other thing I was mentioning, which may or may not be what you were actually talking about, is delete this, is it's like if you had a reference electrode, like there's a thing called the salt bridge where you can have your reference electrode in a completely separate compartment. And this is good if like your reference electrode has, some kind of component or something that could contaminate your system. But like it's here, it's in a separate vessel, or maybe you're heating your test solution up. And this literally, it just goes. This is a little bit of the design that Pine has. It doesn't look like a boot, but and this goes into, say, a fritted tube, like a fritted glass tube, and it's full of solution. So this thing has a solution all the way. It has the test solution. This whole thing is test solution. And then the test solution goes all the way from one thing here. It fills it up and it's exposed to the reference electrode. So sometimes people will say there's a salt bridge, and the salt bridge is just a way of, it doesn't get the reference electrode sensing point closer to the working electrode, but it's designed that, if I'm heating this solution up, or I have or there's a not a contaminant, but like maybe the test solution has something that could contaminate the reference electrode, or sometimes the reference electrode has something that could contaminate the test solution. It's really hard for ions to travel all the way from one side to the other through this. And this is a frit, so it also makes the movement of ions and contaminants much harder and longer. So that's what I thought you meant when you said like a bridge tube, but this is a salt bridge. That's one design for
maybe
it.
Maybe the tube that connects the separate container is called a bridge tube. I don't.
Yeah.
Maybe, I'm not sure, to be honest. That's why I thought it was the same thing. Maybe that's called the bridge tube. And in any case, you've just perfectly described what a luggin capillary or luggin tube is and what a salt bridge is. And so, Zaki, hopefully, just some of that is what you're seeing for bridge tube, because some of these terms, it depends on what you read and what people use. It can vary right across literature or whatever.
Yeah. So Zaki has another. I don't know if we should we answer Zaki's second question?
If it's related, or it can.
It's not completely related, but I figured we'll answer Zaki's questions. Like Zaki asks, how long RDEs could be run without affecting the performance of hardware? So the hardware usually is a potentiostat and a rotator. And potentiostats are just electronics. It's just like a printed circuit board. It's got a heat sink. It just runs on power. A rotator uses a motor, and usually we have these kinds of brush connections that make electrical contact between the RDE and the rotator. So when you ask about how long could an RDE be run without affecting the performance of hardware, it sounds like you're just trying to see how long can you rotate an electrode, and can you rotate an electrode indefinitely? And so the answer is, I don't know for sure. I feel like you could rotate it for a very, very long time. Just speaking anecdotally, we have customers who've had rotators for a very, very long time, and they rarely have to like change the brushes out just because of the maybe the humidity of the location. But it's like mechanical parts are going to start failing when it comes to like just running something for a super long time. I'd say you can go maybe months of continuous use. Don't hold me to it, but if I had to guess, you might be able to run a rotator for months without having to change the brushes and affecting.
Yeah, my general advice to like a lot of folks in the corrosion world are the one, not always in academic labs for RDE. Yeah. You don't, unless you have a really mean advisor or something. Yeah. You have to be in the lab literally 24 hours a day, 7 days a week, all the time. But folks who do corrosion research, they very often have the rotators spinning like literally 24 hours a day, 7 days a week. And in those situations of the maximum amount of usage, the recommendation is typically to change the brushes every 4 to 6 months. So yeah, you're exactly right. It can be used pretty much continuously for half a year. And so people who are using it intermittently, you don't have to, unless something goes wrong or you drop an electrode or a shaft or, like things happen, wear and tear or whatever. Right. But under like normal, proper laboratory practice and safe usage and everything, you can use years, before anything needs any change. Now, of course, practically things happen and it doesn't always work that way. But yeah, I mean, for the most part, the hardware should be workable for years uninterrupted.
Yeah. Let's see. So that was Zacky's questions. Moving on. Chica has a question. Making precise dropcast on peak electrode tips are difficult. Do you have any recommendations as to how to go about it? Because the ink spreads out anytime you dropcast.
I do. This is a very tough process. So the first recommendation is don't use peak. Okay. You have peak, so that's tricky. All right. So in all seriousness, if you're using peak, it's probably for a reason. You probably need it for a high temperature application, or maybe you're using electrodes from another company that only make peak. We might be, to my knowledge, this might not be accurate. It was at some point. It might still be. Pine, I think, is one of the only companies that manufactures Teflon shrouds still. I don't know if any other companies are making them. So a lot of our competitors, for example, have peak shrouds only. And so if that's what you're using, that's one of the downsides, I suppose, right? Is that you only have peak. It's hydrophilic. The drop spreads out. That's tricky, right? To that point, we have some electrodes with a peak shroud where you can change the disc in and out, and the disc sits inside of a Teflon U cup. So it's got a peak shroud and it has a glassy carbon disc you can drop your ink on, but there is a thin cup, basically, right? Like layer of PTFE, of Teflon, around the disc that sits in between the disc and the peak. And so PTFE is very hydrophobic. And so PTFE is very good at keeping the droplet on the disc. So that's one just suggestion generally, is if you're able to get a kind of electrode that has a PTFE barrier between the disc and the peak, that will help. If you don't have that situation, you just have a peak shroud with a disc, my suggestions are basically one of two general things. The first is try, if you can, to reduce the alcohol content of your ink. The contact angle of water is much bigger than the contact angle of alcohol. So for example, if your ink consists of all alcohol, it has a contact angle of almost 0. In other words, it basically completely flattens out. Even on PTFE, it might spread. It's very thin and it's really hard to keep contained. Whereas pure water makes a nice bubble usually, or it's more likely to make a bubble and not spread quite as much. So if you have an ink, a lot of people do like 50-50 water, alcohol, solvent or something like that. If you're able to cut it to like 80-20, 90-10, mostly water, that will help it from spreading, number one. And number two, reduce the volume of your droplet. So typically the droplet size is somewhere between 5 and 20 microliters. If you can get away with reducing the droplet size with your micropipetter, do that. In a lot of cases, it is not necessary to entirely cover the disc with your dropcast. So in the situation where it is almost impossible to keep the droplet of your ink from spreading onto the shroud, it will be impossible to keep it to entirely cover the surface of the glassy carbon, for instance. But that can be okay because, for instance, if you're testing a catalyst for OER or HER or ORR and it's platinum or something, right? Whatever it is, it's probably much better at OER than glassy carbon is. So if you have underlying glassy carbon, that isn't covered, it's fine because that's not going to contribute anyway, right? You do a background on the pure glassy carbon and you get its background, and then you add your catalyst. Even if it's not fully covering the surface, it's fine, because the critical thing is how much of your catalyst is there, which is why you have the problem of it spreading onto the peak, right? If you have some of your catalyst that landed on the peak, then you don't know how much is on the disk, you don't know your loading, and then you don't have any quantitative analysis, right? That's the problem. So if you do drop it and it spreads on the shroud, wipe it away, try again. Don't proceed. Don't dry it with it on the shroud, because you just have an unknown loading. But try some of those things. Try to reduce the alcohol content of your ink if you can, because that makes it spread, and try reducing the volume. Try 5 microliters, 6 microliters. It'll make a really small droplet, but at least you'll know how much is there. And that might help it. And then honestly, it's just practice too, because some of it's a small disc, and you have to keep your arms kind of, it's an arts and crafts project, right?
Yeah.
I always found like I have, I'm not like a surgeon, but I have relatively steady hands. But as soon as you get the pipetter and you're at your disc, you just like, oh gosh, I'm trying to drop it center, and you're like, I don't know if I can get it, So it's hard. It's just tricky, just practice getting that as dead center as you can.
Yeah. Isn't there a paper from a guy who,
there's a friend of mine at the Naval Research Laboratory I used to work with. His name is Ionic. I plug him like at least once a week or once every 2 weeks,
because we get this question all the time.
Yeah, I'll plug his paper. So Ionic is a I don't know how famous he is. I know him pretty well. He's like I say, he's a friend of mine. He has previously published this. At this point, it's like 10, 11 years ago. Papers that are on just the thin film process. And so I always plug his work. To my knowledge, I don't know many other people who have done any or as good an in-depth analysis and publication of the engineering of the thin film. Not just like, here's my platinum on carbon and here's how good it is at doing ORR. He's like, this is how to make the ink, and this is why it's important, every little step, and this is how to make your film as good as possible, and how you'll improve your activity just by making the film better, not by like engineering a better catalyst. So I'm going to plug him again and put Ionic Garcini paper on RDE thin film preparation. So here's a link to a paper that he might have some other papers as well, but Ionic and Karen Swider-Lyons, who I also worked with and know from NRL, published this paper again about 10, 11 years ago. So check that out. That will be hopefully helpful to you as you, again, work on this process.
Very good. All right. So there's 2 questions by FCB. FCB, thank you for being a YouTube member. If I change the concentration of KCl of a silver chloride reference electrode during CV, then what happened to the potential change of the experiment? It's a very good question. And of course, your second question is also proper cell setup for bulk electrolysis. So I'll address the first one. So there will be a potential shift in your experiments, and it's all based on the Nernst equation. So the Nernst equation just states for a redox reaction. Let's just see, everyone can see. So for a redox reaction, the potential is equal to E naught minus RT over NF, and the natural log of the activity, or in this case, we can think of it as the concentration of our reduced species and our oxidized species. For silver chloride, the chloride ion concentration is the important thing. It turns out that you have silver chloride and you have solid silver. Those have activities of unity. They have 1. So chloride ion is the only thing that affects the potential in this case. So the shift is going to be based on this natural log of chloride ion. And so what that means in principle is that for approximately, so for every order of magnitude change in the concentration of chloride, you'll get approximately 59 millivolts, maybe 60 or 40 millivolts of shift in your reference electrode potential. And so that's for every 10x 10x KCl that you have, specifically the chloride Cl minus concentration. So that is what you'll do, and what you'll observe is your CV will look the same, but your voltage is going to shift by about 59 millivolts, again, per every 10x change in the chloride ion concentration. So if it changes by a little bit, if you had 0.1 molar KCl, and then all of a sudden you go to something like 0.101 molar KCl, you're not going to observe a very large difference, because this doesn't represent a very big change in the KCl concentration. So and so even if you have a change of 0.1 to 0.3, a 3x change in the concentration,
It's probably like 15 millivolts.
Yeah, it might be 10, 15 millivolts or something. So, this has to go to 1 molar or 0.01 or 0.001 for you to start seeing hundreds of millivolt shifts in the potential of your reference electrode. So that is so that hopefully answers your first question. And then for your second question about proper cell setup for bulk electrolysis, I think everybody kind of does it differently. A lot of people, it depends on what you're doing bulk electrolysis of. But a lot of people use something like a separated H cell with a membrane, or they have a counter electrode in some kind of fritted tube to make sure that whatever gets generated at the counter electrode doesn't affect what happens at the working electrode. And people use these large kind of mesh electrodes or carbon felt electrodes to electrolyze a sufficient amount of whatever they're specifically looking at. So another thing to do is I would also have a stir bar, because for bulk electrolysis, you want to make sure that you're moving the solution around in such a way that you get the species. Your species is getting in contact with the electrode surface to undergo the oxidation or reduction reaction for your electrolysis. So those are the main things that I've observed. Larger area electrodes, separate the working from the counter electrode, and then make sure you're at least stirring what's going on in the working electrode compartment. And then have your reference electrode close to, nearby, the working electrode if you implement a reference electrode. But there's a bajillion different kinds of setups for bulk electrolysis. It just depends on what you're doing.
We made it about 2 hours.
Uh-huh.
You just got the Nernst equation in.
No, it's okay. I just barely got the Nernst equation.
You barely. That's Alex's favorite equation.
It's
his favorite equation.
If
a live stream goes by and he didn't get to talk about the Nernst equation, he's just sad all weekend. he's just like sad, just crying, and I feel. Thank you for allowing him to bring up the Nernst equation.
So we are running low on time. What do you think? Do we need to call it now, and then the following week or something like that, we'll be able to work on the next set of questions? We have a meeting that starts.
Yeah, we actually tend to go over when we can, but we have other obligations today. Yeah. I think we're gonna have to call it here due to time, unfortunately. We will. Fernando, I see you've asked a question. Cesar, there's a few of these. We'll get these categorized, cataloged, and saved. Actually, for the next couple weeks, I will not be around, but Alex will be. Hopefully, maybe, possibly at some point, we will answer.
In 2 weeks, I'll be around.
2 weeks. Okay, it might be. It might be some time. So I don't know. We'll see what we can do. This is our typical time slot. It's Fridays at 1 p.m. Eastern. You know, Alex did something crazy a couple weeks ago and did it on
I
a
did one on
Thursday.
Thursday. May have to
We
do
could
that
always
again.
do one at a different day and time. Maybe we'll see what we
Yeah,
can
we'll
do.
see.
I hate leaving everybody in the lurch here, you know.
Yeah.
But we will categorize. It's the wrong word. Why do I keep saying that? We will like catalog and
Yeah.
take all the questions that you have asked and try to address them when we can. We do have a way to keep questions, like you said, in our sort of log of this live stream, and we do try to answer them all. We really appreciate everybody asking questions, and the engagement is wonderful.
Yeah.
Thank you all very much. This is episode 5 trillion at this point. I have no idea.
I
We've
have to
done
look
these
up
so
the
many
episode
times.
too.
I feel like I'm a broken record. I say this every week, and we started this over a year ago with very low expectations, to be honest. It's like, hey, if anybody shows up and asks questions, we'll answer them. But otherwise, we'll just talk about movies for an hour or something. So,
episode 57.
This is 57.
This is 57.
Amazing. I'm really truthfully, I'm very grateful for Chris coming back. I don't know why you want to spend Fridays with us, but we appreciate you. And we appreciate everybody who's joins us and asks questions. We really enjoy this, and this is it's helpful for us for our YouTube content and everything. And anyway, just a big thank you as always to everybody who joins us and asks questions. We hope we're helping you with your research, and you're helping us with our engagement, and it's a win-win. So I want to show gratitude whenever I can. In any case, thank you again, everybody, and I hope everybody has a good weekend. We will certainly see you at some point. Sorry, the time in the next couple of weeks is a bit scattered for us. It's a lot of travel and things. But we will do this when we can. And until then, I hope everybody takes care.
Yeah. Take care.
Bye-bye.
Bye.